talk by Agnes, and she's changed her title, so now says Duality and Invertibility using finite resolution.
Thanks. Yeah, when I made my title, it was a title for both talks, and now it's clear what goes into the second.
All right. Oh man, that would be great. No. As long as that makes you reappear, it would be pretty awesome. All right, so I want to first start by reminding us a little bit what we did last time, and then I want to use these things in the rest of the talk. So last time, I wrote E, and this was a generic name for a wedge of suspensions of spectra of the form EHFI, where Fi in G are finite subgroups. So last time the point of the talk was that we learned how to build the learn what it would mean to build the Cannes local sphere out of guys like this, okay? So I didn't give a general recipe because there is none, but okay, so I'll start at the edge. So you start with the Cannes local sphere, and then you maybe map in some well-chosen homotopy fixed points for a finite subgroup, and then you do it again, and then x0, this is an equality, and then you let x1 be the co-fiber of this map, and then you build another map, and then in such a way that you can, so that this composite is trivial, you can extend this, and so on and so forth.
Agnes, do you really mean x0 is equal to e0?
I do. So I'm taking...
It isn't the co-fiber of that map?
I don't. So that was one of the comments last time. So if I took the co-fiber of this map, then I'd be not much further, right? I would have just gotten rid of the kind of the Hurwitz image in this finite thing. So it'd still be pretty far, and I would have this thing would not be something that I understand. So I'm trying to have all the pieces in this side be something that I've got control over. Okay? So now let me put ... E n squared minus 1. And then if you're building a finite resolution of length n squared, then the last step should have, so this should be your xn squared. The last step should be the Cannes local sphere. So now you've got this sort of realized in terms of stuff that you can compute with in theory. Okay? And this resolves into, like, these are all exact triangles. And this resolves into there's one here, and this resolves into a tower of vibrations whose limit is the Cannes local sphere, and that gives you a Gauss-Field-Kahn spectral sequence to compute with. Okay. So in practice, so actually before doing the in practice, let me recall the example that I gave. So P is 3 and n is equal to 2, and I want to touch base with Leonard's talk when I rewrite this. So I'm going to rewrite it a little different. In fact, it's going to be a slightly different resolution, a little thicker. Okay. But here's another example. So if you remember what I wrote last time, then I had built the resolutions in terms of these guys, and then these guys. Well, it turns out that this is LK2 of TMF, and that this one isn't quite LK2 of one like this, but if I take this and its suspensions, that's LK2 of TMF02. Okay, so this is TMF with level structures. These are the same spectra that showed up in Leonard's talk.
What do the hats mean?
So this was just to touch, connect with my last talk. It would be, this is the maximal finite subgroup of S, and then you extend it so that it includes, you extend it so that it's the normal subgroup of a slightly bigger group and then the quotient is the Galois group. That's all. Okay? All right, so, okay. So then I'm going to write something, and it's going to be understood that all is K2 local. Everything I write is K2 local, but I could have changed the resolution just a bit to get something that looked like this. Okay, now I'm going to write the wedge here, and this is for later. This will stay here. So I'm going to write TMF02. I just mean here the wedge of these two spectra. I'm just writing it funny for later purposes. And the map doesn't come out just of this. It comes out of both. But well, let's just assume I have bad board work. Okay, so here I mean to put sigma 48 of TMF wedge TMF 02, and then sigma 48 of TMF. Okay, I think I got all the terms. So this is basically the duality resolution. So I've added some copies of this spectra, but I just make them cancel out. Okay. Right. So this is the sense in which, so these are guys that we know and love. I mean, even if you're not doing chromatic homotopy theory, you might be thinking about them. All right, and then so maybe I just want to say that there's a similar resolution. The one I've mentioned that there exists such a resolution at the prime 2, and it would involve TMF with levels TMF03 and TMF05. Okay. Those are the terms that you would see. And then the last thing I wanted to remind us, perhaps, do I have space? I want to remind two more things. So in practice though, let me write it here. In practice, we do some algebra and we build something that looks like E star, E0, E star, En squared, okay? And these are supposed to be the shadow of a thing like that, and then we choose a map in the Hurwitz image. So we choose a map in the Hurwitz image, let's call it phi I. These could have been the delta i's. That goes to delta I. We look at this, phi 1, phi 2, phi n squared, and then we try to solve the problem of resolving this into such a diagram. And this involves solving a bunch of total brackets and stuff like that. Okay? So in practice, we come at it from algebra, and there are choices involved, and this will come back later in the talk. Okay? And the last thing I want to put on the board, and I'll just put it here because I feel like this is getting crowded. Maybe I'll put it there, and then eventually it'll go. But so one more thing that was built is, okay, so it's nice to use finite subgroups because these kind of spectra are more approachable, but there's also a resolution that doesn't have to do with finite subgroups, and it looks like this. Where Gn1 was a normal subgroup of Gn, which was given by some determinate map, but it had the property that the quotient was isomorphic to the p-adix, and I'm thinking C is a topological generator for this, okay? And I'm going to call this Rn for the beginning of the talk, just because this gets long to write, okay? So basically, this is what we got to last time. Any questions? So it's just supposed to be a recap, refresh your memories. All right. Our memories are activated. Okay, so now I want to talk about these things. So the first thing I'm going to do is talk about invertibility, which in other words is a word for Picard groups. Okay, so what is the Picard group of a, so I'm going to write pic n for pic of SPCan. Remember, this is the category of CAN local spectra. And what's in there? It's isomorphism classes of objects which are invertible with respect to the smash product. And again, I mean the CAN local smash product. And sometimes I will not CAN localize, and I always mean CAN localize your smash products. Okay? So just to give you a feel like how much stuff there is, so pick 1 is ZP cross Z mod 2P minus 1 if P is greater or equal to 3. Not much bigger than 3, but and it's Z2 cross Z mod 4 cross Z mod 2 if P is equal to 2. And these are results of Hopkins, Mohold, Sadovsky. So the pick 1 stuff I'm going to talk about is from these 3 authors. And I want to, so these are all the invertible objects with up to isomorphism, which is weak equivalence for the smash product. And let's contrast. If you look at the Picard group of the category of spectra, then you just get Z. And this is just like generated by S1. Maybe this is a better notation. Okay, so there's a lot more stuff there, making them interesting for the computationally minded mind. Okay, so I want to, okay, no, I'm not making the remark. First, I'm going to state the theorem. Okay, so I need to give you some, remind you of some, so HMS for now is going to be these 3 authors, okay, of some basic things about the Picard group is, okay, so X is in pic n, if and only if, well, this is the CAN local Picard group, so the CAN star homology should be able to tell. So if CAN star of X is free of rank 1 over Kn star. Okay? The way I built CAN, it's a 2-periodic thing, so it's either Kn star or shift by 1. Or there's another statement, if and only if En star of X is free of rank 1 over En star, and the lie is that this is, and I'm going to do it once, I will never write En star if I don't mean the following, LKN of En smash X. Okay, this is not a homology theory. It's not the homology theory of the homology of X. At least if X is big enough, it's not. So, but that's always what I will mean. Okay. So why? I mean, this thing is really nicely, like En star of this, if you can localize, has a connection with the Morava, a strong connection with the Morava stabilizer group. So that's why we consider this object. It's more computable. Okay, so now the remark. So I'm going to take, if H and G is closed, so for example, H is Gn1, which is over there, or finite. These are the examples that will show up in this application. Then Kn star of ENHH is, so continuous functions from Gn mod H into Kn star. And similarly, En star of ENHH is the continuous functions from G mod H into En star. So this seems to have been folklore for a long time. If H is the trivial group, the proof that I know is in a paper of Hovey, and if H is closed, then it's in a GHMR. Those are places where you can find the proof. Okay? So, of course, Hopkins, just splatter it all over the boards. We cannot say Hopkins often enough, okay? So now that I've put all the ingredients on the board, I want to use it to construct elements, give you tricks to construct elements in the Picard group that use finite resolutions, okay? So first we're going to use this guy, the one that's over there, okay? So the art of twisting resolutions. That's going to be the next subsection. Okay. So I'm going to take lambda in pi 0 of Rn star. Okay? Rn, let's remind ourselves, is this thing. So then, okay, we have a resolution Rn, and if I put -1, then I'll put the Can local sphere there, okay? But the idea is you change it with an element. So an element of this you can upgrade to a map from Rn to itself, because Rn is a ring map, sorry. So you can turn it into a self map. And the idea is that if you look at this, then you'll get something which I'll just call S lambda. And this S lambda is going to have, so this idea here was used at height 1 to compute the Picard group by Hopkins, Mahal, and Sobolewski. And then, so where I know a proof of this proposition, and you're going to go in there and you're going to be like, his Rn is not really your Rn. I know, if you're reading the paper, then you'll come to terms with this, okay? But essentially, if you see Westerland, there's the MJ paper, there's a proof of the following fact, is that, okay, S lambda is in pic n, okay? And in fact, there's also, let's see, and so this process gives, to pic n, gives a group homomorphisms. Okay? The idea.
What was this meaning of psi?
Psi is, okay, so psi is the topological generator of this quotient. Take your pick, okay? It's going to always, I'm only going to use psi to denote that, so it's always going to mean that when you see psi, okay? And what's the idea of the proof? So you can actually sit down and do this proof if you have all the ingredients, is you apply Kn star to this, okay? And you use this, and then using star, which in this case ends up looking like from Zp to Kn star, okay? And then using this to show that Kn star of S lambda has rank 1. Okay, and that's often the trick. You realize something, so you have a resolution. It used to realize the sphere. You modify it, but not enough that it changes the rank of the thing it's realizing. So then you get something that's in the Picard group. Okay, so you just twist it a little bit, and then you get really, really sneaky. You twisted more, like in more and more subtle ways, so that Kn star and En star see less and less of the difference. Okay, so what is that? So this is a comment that was sort of foreshadowing my next page. I saw a comment on my last page. So I think this is injective, but last night I couldn't remember the proof when I was doing my final prep. So I'll leave it at just a map. So is it injective? Make it a question, right? If you're not ready to make it a conjecture. Okay. So, okay. So elements in the Picard group don't all have like equal dignity, I guess, or like something. They're not all equal to our minds. So we had pic n, and there's another group which we call pic n alg, and that's the Picard group of a category which I'm going to denote like this. So roughly this is twisted. So this is E star modules with a continuous GN action that's compatible. Okay? These are called Morava modules and may come up later. Okay? Well, so there's a map that goes this way, and it takes an element x, and it takes it to E star of x. So the action, again, this was pi star. I said I wouldn't say it again. Here I go. So there's an action of Gn in there, and that's where it gets the twisted action. Okay? So this is an algebraic gadget. As topologists, we go, we're like, I want to know about the kernel. Okay, so that's the definition of kappa n, is that it's the kernel of this map. Okay, and these are called exotic, although we will see later that this is a strict cast. Even exotic elements don't have equal dignity. So you get a diagram like that. And in here, I just want to put one more thing in. I'm going to write pic and not. Remember, x is in the Picard group if this is free of rank 1. Well, it could have been a shift, but if it's not, then we put it in pic and not. Okay? And then similarly, this category has a similar thing. Ouch, and there's a map. And kappa n. And why do we go? It's because this is h1 of gn e0 star. And even though we have absolutely no idea how to compute this in general, we still act like if it's the easy part. And honestly, if you do these computations, this is not easy, okay? But that's the thing, okay?
You know what that map on the right is onto?
Aha, I knew somebody would ask. I don't know. We don't know. In fact, this is one of the parts of, so current work in progress by Paul, Hans Werner, Irina Bobkova, and myself is to compute kappa 2 at height, pic 2 at height 2. Hans Werner's done most of the work to compute the algebraic Picard group, and we don't know. We can't show that it's surjective yet. Mysteries. Okay. So, unless something happened in the month that I wasn't here. But then, all right. So, you see this nasty p-adic stuff? If you think p-adic stuff is nasty, you're probably in the wrong business, but it comes from, so this is where this, the p-adic summands come from. And stuff, but like roughly, so this is, they come from this, the big p-adic stuff. This, in practice, I say in practice because we don't know in general, in practice is a finite p group. Okay? We know that it's...
So when you say p-adic summands, you mean free CP1?
Yes.
I was being, like, the fact that that's big comes from this, okay? And this in practice has been finite in all known examples. So I think a herd proves somewhere that it's p-torsion, but the finiteness is still to be determined. So example, kappa 1. So if I don't write kappa, it means it's 0, okay? So if you're like, where is it? Unless it's higher height. So at height n is equal to 1 and 2. So if p is equal to 2, kappa 2 is zima 3 cross zima 3. If p is equal to 3, and I'll talk more about that. And kappa 2 has order 2 to the 9, okay? So this is GHMR, and I guess Shimomura, Kamiya, and kappa 1, this is just like this theorem, it's a timeless fact of life. No, I'm just joking. This is HMS. All right, and this is work in progress.
That's for p equals 2.
2, and it's myself, Bobkova, and GH. GH will mean Gers hen, unless it's Gross Hopkins. Then I will write Gross Hopkins. Okay. Okay. So that's to give you a feel, and now I want to talk about how do we twist resolutions to produce elements in there. Okay? So there's a variety of tricks in our bags. So the first remark is that suppose that En star of lambda, and now I'm going back to this lambda here. Lambda as in like, let's do a symbol like this. Suppose that this is the same as the En star of the identity. Okay. Then if you look at En star of this thing, then on En star module, it's not going to be doing anything else, anything different than what you did for the sphere, and you're going to get that En star of S lambda is En star as Morava modules. Okay? So you're going to get that S lambda is in K pa n. Okay? So example, n is equal to 2, p is equal to 3. My example today is n is equal to 2, p is equal to 3. When it's not, n is equal to 1. So let's see, pi 0 of R2, in this case, let me start with pi 0. That's z3 times z mod 3. So if I take units, you end up having z3 times cross z mod 3. Okay. This stuff is the stuff of Adams-Novikov filtration bigger than 0. This is all A and F is equal to 0. So En star sees this. This is in the image. En star of anything that comes from here is seen by En star. But if I call this tau, then I get, so what's here, it's like 1 plus tau. Okay? This stuff, En star doesn't see tau. It kills tau, so it doesn't see it. So if you do S of 1 plus tau, then, so this is R2, C minus 1 plus tau, R2, then this is going to be an exotic thing. I'm going to call it Q2. Okay, that's going to be the definition. And let's see, at some point, so this construction, so this is GHMR. And okay, so Q2 is in kappa 2. Okay, so that's the conclusion. And in fact, so this is where the hierarchy comes. Q2 is super exotic. Okay, this is a technical word. And what does it mean? So what was R2? R2 was E2HG21. And if I smash it with Q2, well, that's like if you want to find out what happens, you just smash R2 here, and you have a map there, which is going to realize an equivalence between these two things. Okay? So, in other words, Q2 here is invisible to E2HG21. Okay? So, if you're invisible to E2HG2, then it's because you're the sphere and you don't recognize yourself in a mirror. But so this group here is really big. It's almost all of the Morava stabilizer group. Okay, roughly this is the center. That's not always a true statement, but like roughly this is stuff whose action we actually understand pretty well. Okay, what I said was true if depending on P and N. So this huge finite subgroup doesn't see that this is exotic, okay? So it's hiding really, really deep in the Picard group, okay? The contradiction, well, not the contradiction, maybe the weird thing is that somehow the super exotic stuff is not so hard to construct, okay? It's weird, but it's not hard to construct because this trick just works generically, okay? So if p is equal to 2, for example, so you'll get that the super exotic. Well, first, I realize I didn't even say it. So p is equal to 3, the super, let's call it super kappa n, just because, is z mod 3, because it's all the stuff that comes from this sum n. And if p is equal to 2, the super kappa n is z mod 4 cross z mod 8. Okay, so that's not necessarily such a, I mean, it's as hard as computing pi naught of this thing, which can be quite difficult, but at least we can characterize it. Okay, so.
First statement is for n equals 2, and the second for n equals 1. Oh, they're both n equals 2.
Yeah, so isn't it weird that I didn't start with n is equal to 1? Yeah.
Are you missing a unit sign in that middle term for pi 0 r?
I put the brackets, but I never xed it. Is that it? Okay. Sorry. Yeah. Yeah.
Let's see, kappa 1 for odd primes is trivial.
Yeah.
And what happens for kappa 2 at large primes, bigger than 3?
0.
0.
Yeah, so I mean, maybe it's, I mean, I should have probably set that somewhere, but so kappa n, when you're in the algebraic setting, kappa n is trivial. So, like, to be exotic, the E2 page of your Adams-Novikov spectral sequence looks exactly the same as the sphere, so you need a target for your for 1. You need a target for the differential on 1, otherwise that survives to an equivalence with the canonical sphere. And if you're at odd, there's no, if the prime is large, there's no target, okay? Okay. So it's weird that I started with n is equal to 2 and p is equal to 3 rather than n is equal to 1 and p is equal to 2. And I guess if n is equal to 1 and p is equal to 2, there is no exotic. There is no super exotic stuff. So now I get to say my joke. Maybe I won't. So I named the file super exotic stuff and in Dropbox, and I was working on it. So I work in Dropbox, and so some people have like the ding on the like in the corner of their computer, it says ding, and then I guess apparently Hans Werner was sitting there and his screen was going super exotic stuff. Yeah. I didn't change the name of the file. All right, so why is that? Well, pi 0 of KO is just, so here I mean 2 completed KO is C2. So wait, that was maybe too quick. Why KO? KO is E1HC2. So which is, this is 2 completed K theory. Sorry, I think I jumped ahead of myself in my example. So, okay, let's make sense of this statement. So, what's C2? So, G1 is Z2 cross, I'm at the prime 2, which is Z2 cross plus or minus 1. I'll call this C2, okay? So, if I look at the kernel of the determinant, which is an isomorphism, modulo the torsion, so this group here is what is G11, okay? So it's actually finite in this case, okay? So this is the guy which I've been calling R1 in this talk, okay? So pi 0 of R1 is pi 0 of K22, which is Z2, and that's all Adams-Novikov filtration 0. It's all on the 0 line, okay? So there's no super exotic elements. All right, nonetheless, we see that kappa 1 is Z mod 2, so there is an exotic element, so let's explore that one. Okay, I think I'm going to keep this one for one more board. So let's see. So the theme is twisting resolution. It's still there. So we've got this resolution. Let's rewrite it. So I just said that R1 was KO, so I'm just going to write it like that. And let me pick a topological generator for Z2. I'm going to just pick 3. Okay, so that's going to be psi. I'll call it psi, but you can think of so how can you think of psi? So G1 is acting on complete K theory. It's the Adams operations. Okay, so it's all from a familiar context. Okay. So you've got this resolution, and this is the one that we're going to twist. Okay, now I go back to this board. Resolution are born often this way, so maybe what you had first was, okay, so E1 star goes to E1 star of, this is EHC2. I'm going to rewrite it below, so goes to E1. I just want it to look like what's on this board, C2. Okay, so now on this board and this board alone, K is going to be two completed K theory. I just want things to look familiar. So this is K star, this is K star KO, K star KO, and then we've got C minus 1. Okay? And we've got this algebraic resolution, and this thing is supposed to be a shadow of this. Okay? But there are monsters in the world who project a shadow similar to that. That's the shadow. But really behind the shadow hides something. So let's see, where's the monster? Okay. It's so this thing is isomorphic to sigma 4 of KO. And in fact, that's Asimorova modules, okay? With everything that algebra knows, these things look the same. Okay? And so this is K star of the map, right? So if I put K star of sigma 4, 3 squared C minus 1 here, somehow what you put here might depend on your conventions of how C acts, okay? So, but this should work. Then this is an exact sequence. They're zeros, we're in algebra, okay? So you could have decided to realize this instead by using, so what's happening? I say we start with that. We want these to be certain things. We try to lift this. There might be different choices here. There might be different possible realization. And when we're trying to do the sphere, we're pretty strict about what we're going for. But then if you go back and you remember, wait, I could have built other spectra by making different choices, then you get further, okay? So you can realize this so sigma 4 C minus 1 for KO. And let's call the fiber P1. Okay. And so you do the computations of how we got to it, gives you that P1 is in kappa 1. And also P1 smash KO is, well, you have this map, you could smash with KO and then multiply, and this gives you an equivalent to sigma 4 KO, which, let's note, is not KO, because Bott periodicity is 8 periodic on real K theory. Okay? So KO sees P1, okay? So it's not invisible to the eyes of KO. And KO is E1HC2. This thing was finite. And I think the philosophy behind the term super exotic is that if a finite group sees you, you weren't well hidden, okay? So you weren't that exotic after all. Unfortunately, it seems so far I've found it harder to construct these types of exotic guys. Somehow you have to twist these resolutions in non-trivial ways. Here it was kind of given to you, okay? So that's another trick for twisting the, so what's the philosophy or the idea is that you can produce new spectra by changing the realization. Okay. Okay. Okay, so let's go. So I won't give you much detail on this, but I still want to get it on the board so you can stare at it. So if p is equal to 3 and n is equal to 2, okay, well, we had our resolution, which is over there. So TMF, everything is K2 localized, goes to TMF02, TMF02, dot, 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 goes to sigma 48 of TMF. Well, so observation is that if you do E star of TMF, that's isomorphic Morava modules to E star of sigma 48 of TMF at the prime 3. Okay? So here, instead of picking these things to be TMF themselves, you could have shifted them and still be looking at, and maybe there would have been, for some shift here, maybe there would have been a choice that seemed like delta I when you took E star homology. So color, color, color. All right, so you've got, okay, so I had given names to these maps. So maybe this was P1, P2, P3, P4. So here we have, so we started with P1, P2, P4. But okay, so this was a choice of realization. Instead, we could have put sigma 48, and then I guess this gets to 96. But these maps won't do, so you have to make different choices for maps. And then you play the same game with sigma of x1, but x1 won't be the right thing. The cofiber will be some other spectrum. So then this tower will look different. But you know, at the end of the day, you'll finish into sigma 4 of something which is not the K2 local sphere, but a spectrum that we'll call P2. Okay, so this problem is all solved in GHMR. So this is again. So then you would have put P2 at the front, and that's going to be the definition. Okay? So you just get creative about how you realize these things. These are not easy. You have to check that everything works out, but it does. And then by construction, P2 is in kappa 2, so the process does not affect the Morava module. And also P2 smash TMF, well, you have a map here. You can do the same trick. It's going to give you that it's sigma 48 of TMF. That's going to be an equivalence. So it is not super exotic. Some finite subgroups, homotopy fixed points with a finite subgroup, detects it. Okay? And now the fine little theorem is that P is equal to 3, n is equal to 2, is that kappa 2 is Z mod 3 cos Z mod 3, and this is generated by, say, Q2 and P2. Okay? And this was, I think that Shimomura and Kamiya already knew about one of these summands. Okay? This one? P2, yeah. The P2, yeah. Maybe they knew about the other one secretly, or in there. It came to them, but they didn't believe in it because it was so exotic. Okay. All right. So now maybe I'll just say it in words. At the prime 2, there's another trick that comes in, is we don't change the top, but we change the tota brackets. Okay? So we change these sort of factorization here so that the x's become different, although everything else looks the same. So even more sneaky. You can get really, really sneaky with this stuff. Okay, so that's it for invertibility. Now I'm going to talk about duality, and they're very related, so that's why. Oh, I wanted to keep that. Let's just keep it. Okay. I think that's it. All right. Okay. So, and I'm also, these are a specific topic, but I'm hoping that it's also conveying sort of how one does chromatic homotopy theory in the process, and if you're computationally minded. Okay, so duality. So we talk about two dualities in Cannes local homotopy theory, at least two dualities in Cannes local homotopy theory, and two that come up is Spanier-Whitehead duality. And the other one, I guess, we can call Gross-Hopkins duality. And this is, okay, Brown-Kamenitz duality. Duality, okay?
Those really aren't the same.
Huh?
Those aren't the same.
People.
Well, that's why I'm not calling it Brown-Kamenitz duality. It's like Brown-Kamenitz comes up. I call it Gross-Hopkins duality. Okay. So I've heard it called Brown-Kamenitz duality. So dn of x is so you do the same thing as you would do with usual Spanier-Whitehead duality, except that you dualize with respect to the Cannes local sphere. Okay. So and in this thing, dn of s naught is just Lcan of s again. Okay. So again.
I'm making the point that
Yeah.
Spanier-Whitehead in duality and Brown-Kamenitz duality, they're just constructions. Gross-Hopkins duality is a statement that two things are dual to each other.
I see. Okay. Fair enough.
But sorry, can I say?
I want to.
Isn't there also something called the Gross-Hopkins dual?
Yes.
Okay.
Yes.
There is, but maybe the very small parentheses should be larger, not to be confused with the Brown-Kamenitz dual. It's like a Kn local analog of Brown-Kamenitz dual, because it doesn't agree with the Brown-Kamenitz dual.
That's.
Why don't we get some definitions on the board?
I will, and I'm going to say that I think we should call it Gross-Hopkins duality, because as a student, it having called Cannes local Brown-Kamenitz duality always made me think that you just can localize the construction, and it doesn't work. So, okay, so definition, so In of x, we're going to write, is going to be the function spectrum from N of x to a spectrum called IQ mod z. I will say what these are, okay? And Mn of x is the fiber of, so remember Ln was localization with En, remember all the E theory? And there was a map to the lower one. So Mn is called, this is called the monochromatic layer. Okay? And so In denotes In of S naught, okay? Which is functions from Mn of S naught to IQ. Oh, I didn't say what IQ mod z was, okay? And IQ mod z, I'm going to define it by its homology theory. So there's a homology theory that takes x into hom of pi star of x into q mod z. So you can check that this satisfies the axioms of a homology theory, cohomology theory, of a cohomology theory, and it's represented by IQ mod z. It's the spectrum that represents it. Okay? And just like we call this Spanier-Whitehead duality, I mean, I put this under the umbrella of Gross-Hopkins duality, okay? And this is often called the Gross-Hopkins dual of the sphere, and this is called the Spanier-Whitehead dual of the sphere, which happens to be the sphere again, okay? So, theorem of Gross-Hopkins, and that might be what you want to call Gross-Hopkins duality, some of you. So I'm going to say it this way. So In is in pic n. Okay, so In is an invertible object, and in fact, okay, so I'm going to say three statement. If X is a Cannes local spectrum, then In of X is Dn of X smashed with In. Okay. So Spanier-Whitehead duality and Gross-Hopkins duality in the Cannes local category are extremely related. Okay? And finally, this dualizing object, In, is, okay, so there's going to be a Schiff, Sn squared minus n, smash a spectrum that I'm going to call S-det, smash something I'm going to call Pn. So S-det, you need to give it a precise definition to determine Pn, and I won't, okay? But one way to do it at odd primes, for example, is, you know, you twist, you construct one of these and you kind of twist it, okay? So you can also do it using finite resolutions. But maybe I'll say that En star of S-det is En star det, whatever that means, and that means just like you twist this by some character. So G det of X is G of X, the usual thing, and then you multiply by det X, det G. Okay? And finally, Pn is in kappa n. So Gross-Hopkins compute the En star homology of this thing and prove that it has this type, the same as the En star homology of that. That tells you what In is, modulo some twist by some exotic element. And that's the thing I'm going to call Pn. And it is not a coincidence that I've been calling other things Pns. Okay, so that was planned. So let's see. I think that I will just use this. Okay. So, okay. So maybe the remark is that if f is finite, then if you do I n EHF and D n EHF, these are approachable. So they're becoming more and more approachable. So we have a bunch of computations that preceded, I think, the I2 and D2 computations, and we're using them. So P is equal to 2 and N is equal to 1. I1 of KO is sigma minus 3 of KO. D1 of KO is sigma minus 1 of KO. Okay? If P is equal to 2 and N is equal to 2, I think I can't write here, and I think I will manage not to, then I2 of K of TMF is sigma 22 of TMF. D2 of TMF is sigma 44 of TMF.
You've entered the invisible zone.
Well, so where do you stop seeing?
That's about it.
Okay, well that's sigma 22. Can you see the number? 22?
Yeah. Well,
44.
we heard you.
Huh? Okay, well that's 22, and that's, can you do this? Yeah. I'm running out of time. I won't, I'll try not to write more this way, okay? So, at P is equal to 3 and N is equal to 2, it's the same, okay? Wow, that's cool, one might say. Astounding, okay? So why, we don't know, okay? I mean, there's a globality to TMF. Maybe it has something to do with it. Maybe the numbers just worked out. Yeah, okay? So, but okay, so this is Stoyanowska. That was, I think, her thesis. What a great thesis, okay? And this is a recent result by Bobkova. And for now, I'll just say these are timeless results because I don't know who proved them. So they made it to the history of mathematics. So if you want to know more about this stuff, you will if you go to Vesna's talk. So you'll learn how these are becoming more and more attainable.
Minus 5, right? Oh, minus 3. Okay, minus 3. Okay.
Yeah, I picked -3. It was a pedagogical choice, but I will never get to the pedagogy that justified it. I'll do this. Oh, this was the pedagogy that this. I don't know how to say that word, so that's why I'm saying it wrong. Okay, so let's see. How might you get to, if n is equal to 1, I'm going to say this quicker. I wanted to say one thing before I finish. So if n is equal to 1 and you wanted to compute I1, so that's supposed to be s 1 squared minus 1 smash s naught det smash something that I call P1, and I have a P1 here. And let's say that this is a theorem, these are the same, okay? So that's the right P1. This thing, you can, if I find it, you would see that it's S2. And this thing, well, it's S naught, okay? So how might you get to this? Well, you could have taken this KO, and okay, so I'm going to say this is going to be an exercise, is apply sigma minus 1 of I1 to this. Maybe do it extended so that you see what's going on. Okay? Then you'll flip all the maps, okay? And you'll get a resolution, and at the end here, you'll get at the end here, you will get, I don't want to get I1. You'll get maybe we don't do that. And we see that we have I1, KO, or sigma minus 1 I1. I might have just screwed up the suspension. And then here, so this changes the maps, changes the map. I1, 1, and what do I get at the end? Thank you, that's what I want. So if you see it, then that's perfect. Of I1. So AKA, this would be the candidate for this, okay? And now, if you think about, if you plug in my formulas that are over there, the sigma minus 3, and you play around, you'll see that you get a sequence that looks a lot like that, but is a little different. Like the map here is like twisted, this is different, this is different. Do the exercise, check the numbers, you'll get that the fibers are homotopy equivalent, okay? So that you could have just applied I1 to the duality resolution to get this. So if you want to do I2 at the prime 3, then you have to work harder, but the finite resolutions, they come in all over that proof, okay? To construct the different possible, so what are the possible twists? There are powers of Q2 and P2, and you use the duality resolutions to figure out which ones can be there, which one can't be there. At the prime 2, so I think that Jakob Pham, a student of Hans Werner, is applying I2 to the duality resolution and getting new results about Brown-Combinate's duality, or Gross-Hopkins duality, whatever you want to call it, at the prime 2. And now the last thing I want to say, so I'm going to skip all that because I want to get to something else that I just want to put out there. Maybe, I don't know how known this is. Let's not go to that board. Okay. So one of the things that comes into these things is computations of Mark Barons that uses techniques that are similar, same, but different. There's a conjecture, so I'm going to say this quick, and that's okay, of Mark, and it's a theorem at n is equal to 2 and p, if capital N is equal to 2 and p is equal to 3, you'll see what this is. And it says that there exists an E-infinity ring, Qn, such that, and a fiber sequence, which looks like dqn to lk2 of s to qn, okay? And this qn is going to look familiar. Qn is the totalization of so this is the building complex business. Qn is the totalization of TMF, which TMF 0n, TMF 0n. Okay? That's a theorem. So at n is equal, at the prime 3, you'd put n is equal to 2. And it's a theorem there. And here, you see a connection, you see this, right? So this is supposed to be like Q, and there's a similar formula for dq, and this is supposed to be related to it. And we've got that theorem and this resolution, and my understanding is that we don't actually understand the connection, okay? So something's staring at us, but we don't know how to take this and glue it together to get the finite resolution there. So there's like a lot of geometry going on behind this specific resolution that, you know, looks for students to go and think about. Okay. Sorry, overdone.
Thanks for the challenge. Are there questions?
Does C4 go into the resolutions at the prime 2?
TMF 05, yeah. So at the prime 2, so you can build the duality resolution which has TMF 03 level structures, but then you can't, so you can do it for R2, for half the sphere. You can't upgrade it to the full sphere. So what you need to do is you take a centralizer resolution of Hans Werner. You take like one type and this type, and then you mix them together. And then you'll get like, it starts with TMF, and then the next map is exactly what you guys wanted, TMF 05, TMF 03. Yeah.
I mean, I guess I was asking if sort of exotic Picard elements of E2 homotopy fixed points with C4 appear in exotic
So,
Picard elements.
so if you're detected by, if EHG24, if TMF sees you, so there's a Z mod 8 that TMF sees in the exotic Picard group. And somehow TMF subsumes C4 because it's a subgroup. So like so we already can approach like who does TMF see? We don't need to do like who does smaller guys see. We do like maximal finite subgroup. Who does TMF see? And then we move on to who does this guy see? Yeah. So we just don't need that step. Yeah. Because of you. Yeah. Yeah.
Are there other questions? Then there should be coffee in the lobby, and we'll reconvene at 11:30. Thanks.